right, with that, I'd like to introduce Amy, who's a professor at University of Washington. I'm honored to have been mentored by her a bit while I was spending time at University of Washington. Her insightful questions are the best, the most amazing, I tell everyone. Her work focuses on equity in computing education and harnessing the power of computation for good. She crosses a variety of exciting research communities that are really relevant to those of us on the call here today, in particular HCI, software engineering, and computer education. And with that, I'll hand it over to her.
Great, thanks for the intro, Sarah. I'm gonna go ahead and share my screen and press a bunch of buttons, so apologies for the transition here. Like Keela, I'm also calling from the West Coast. I'm in Seattle, and so it's 7:38 a.m., which is a wonderful time to be speaking because it means you get my mind that's fresh. Let's see. Presenting, captions on. Okay, you should see all of my mostly translated words now on the bottom of the screen. So I'm going to call this talk today Studying Programming Through Making. And those words I've chosen really intentionally, partly because I want to talk about what it means to study programming, but also what it means to do that while also inventing things and creating tools that, that we want to use to transform what programming is. And so I'm going to try to talk about how we do this through a story of telling my dissertation. And I thought that would be the most resonant, just because many of you as students are working on things like a dissertation or starting graduate school and trying to think about how to do that. So I'll give you some insight into some of the struggles that I faced in making choices, but also how I chose some of those decisions with other people's help. So here's a bit more about me, just so you understand where I am and how I got here. I started as an undergraduate in computer science and psychology. This was back in the late 90s. I stumbled into research after following a hot pink job ad for a summer research position that I had no idea what it was. And that was with Margaret Burnett, who was studying spreadsheet testing. And I did my PhD later at Carnegie Mellon University with Brad Myers, who is an HCI researcher. And I started publishing in HCI, but then also in software engineering after I stumbled upon some other mentors at Carnegie Mellon, Jonathan Aldrich, and then Gail Murphy, who was at the University of British Columbia, who joined my committee. And so after grad school, I joined the University of Washington's Information School and really published a lot in tools and studies of programming in HCI and software engineering and in computing education, really always about productivity in programming and really trying to make people more productive in teams. And then I started shifting over to doing things more about learning instead. So these days I think of myself as a computing education researcher who applies things from programming languages, software engineering, and HCI methods and ideas into the learning and teaching of computing. So I've been in lots of different fields and thought about different methods and epistemologies that fields have had for quite some time. So this talk really is trying to answer this basic question: how can we learn things about programming through the things that we make, right? How do we use the making that we do as a lens into understanding what programming is? So if you have a programming languages background, you're probably used to things like proofs and maybe some benchmark studies to understand what it is that we've invented. But there are lots of other ways of knowing. There's observing what people do, there's asking about people's practices, there's theorizing about behavior and cognition and social contexts. And these are the methods that most of academia uses to try to understand the world. And this includes HCI. And this is where progress comes from. And so the general argument of this talk is that programming languages should be open to using these methods as well. And they're really an essential part of progress in making sense of what programming languages and all of the other underlying techniques are. So there's 4 things I want you to take away from this, and we'll come back to these at the end of the talk. One is that user studies are not just a box that you check for publication, if that's even required where you publish. More broadly, they're really a way of deciding what to make and understanding the significance of what you've made. And so I'm going to try to give examples of that. 2, one study is really not enough to understand something. If it takes a dozen to believe that a drug or a vaccine is safe, why would one be enough in computer science to believe that we understand what a particular invention is? And so I'll show examples of how I learned things over multiple studies. 3rd, study design is really situated and highly complex. We have to take it slowly to really do it well and to understand what we've done. So I'll give examples of me not doing it so well and having to do another study to try to understand and deepen my knowledge of something. And then lastly, since HCI is in the title of this workshop, just the point that HCI is more than user studies. It's a massive research area with hundreds of sub-areas and tens of thousands of researchers, all inventing the future of interactive computing and its impacts. Programming is this little tiny sliver of it. Some of you have probably already encountered that, realizing that if you go to the conference like CHI, you might find 5 or 10 papers that touch on programming, right? But you're gonna find 500 papers about other subjects. So broaden your understanding of HCI. So this is how we'll talk about those learning objectives. I'm going to talk about my dissertation and break it into sort of 5 phases of my understanding. And I think you'll see my understanding mature over time. And then we'll return to those learning objectives and reflect. And then I'll share some resources to help you learn more about doing user studies. So part 1, what is debugging? And I put 3 question marks here because I really had no clue. I just started graduate school. I was really vaguely interested in making programming easier. I didn't really know what that meant. All I knew is that I wanted to build things and make things that help programmers productively express their ideas. So that was my general vague goal in research. And so Brad, my advisor, he suggested that I go watch some people do some programming and see if I could find some opportunities to make something and invent something. And this was his sort of casual approach to thinking about research is, I don't know, go understand the world and then go invent something cool and tell me when you have. He didn't really suggest that I go read anything, which I thought was surprising because in my disciplinary training, right, in psychology, we read a lot. In computer science, we didn't really read at all. And so I had this conflicting motive, and I spent about a whole semester reading hundreds of papers about the psychology of programming and leveraging a literature review that his former PhD student had done in his dissertation. So that was equally formative to my understanding as doing some of these observations were. So what did I do my first semester in terms of observations? Well, there was this really interesting class that the late professor Randy Pausch had been teaching called Building Virtual Worlds, where he brought together artists and sound engineers and computer science majors. And they used a platform that he had been working on called Alice to help people come together as teams and make interactive virtual worlds. And the developers on those teams often had to build the behavior that the designers and the artists had envisioned. And so I watched the developers. They'd write a line of code, they'd test it. If it wouldn't work, they'd get frustrated and confused and lost. And it didn't really matter how careful they were. Their programs were always molded through iteration, right? They never wrote it perfectly the first time. So this is just like any other kind of programming that you're all familiar with. Here's a picture of one of those developers whose screen that I took a picture of. He was trying to build a Monsters, Inc. game with his team, and there was a sound engineering student and an industrial design student, and they were really trying to get this very precise animation to work, triggered by a particular event. And so I spent about 30 hours just watching people program in Alice, and a lot of things became clear. One is that debugging was not this peripheral activity. It was this activity that really dominated programming and drove it forward. That was really key. And then the way that people did debugging was driven by guesswork. If you look on the quotes on the right here, things like, why did Sully move? Well, maybe it was the do together statement that I just wrote. Let me try undoing that. And then 5 minutes later, nope, it still happens. And then another guess. Maybe it was another event. Let's disable it. 5 minutes later, nope, it still happens. And so there was this process of reasoning through possible explanations of what had happened at runtime and then testing them. And what I observed through all of those 30 hours is that most of the time people's guesses about what was going on were wrong, right? It took them a long time to find out. And then they had to think through their guess and then find another hypothesis to go investigate. And what I saw in all of this reasoning is that the only judgments that were really sound was whether the output was wrong, right? They knew whether what they saw on the screen was correct or not, but they didn't really know even things that had just come before that output being generated, whether those were wrong. And sometimes I even observed cases where people's perception of the output was wrong. They thought something had happened, but it hadn't. Or they thought something was wrong, but it wasn't wrong. So even that wasn't really trustworthy information. So I wanted to study this more closely. So I had several students come in and try to build something that, that I had specified and then recorded them. And so I watched 12 hours of video recordings very, very closely. And the sequence of this activity was really clear. The developers would be writing some code. They would inject some defect without knowing it, of course. And then long after they'd created that defect, they would notice some failure. It might be directly caused by it or indirectly caused by it. And their guesses were very much shaped by what they had just done. There was this recency bias, right? And the defects were rarely recent. And so that's where debugging work came from, was the lack of recency of where that defect had been introduced. And so eventually, after laborious guesswork and correction of their mental model of what they built, they would discover the defect. So here's a screenshot of a participant realizing a defect, creating one without realizing it, noticing a failure 30 minutes later, and spending the rest of the 90-minute session trying to localize it, right? So this was not just some isolated episode, it turned into the entire 90-minute session where they were programming. And so in that first phase, when I was just watching, note that I hadn't really thought about tools at all yet, right? In HCI, understanding problems requires really stepping back from the making and thinking critically about the contexts in which that making is happening and the tasks that people are doing and the dynamics of what's going on in their head in relation to the medium that they're working in. So really what I was doing here was a kind of science, right? I was observing and trying to understand what was happening in these debugging contexts. So if we move on to the second part, this is the aha, right? This was the design insight. So this is the making phase of what I was doing. So what were the implications of what I had observed? Well, if most debugging tools assume that a developer knows what code might be wrong because, for example, they say, choose a breakpoint to set, right? Or choose some code to analyze. But that assumption was usually wrong. What does that mean, right? It means that no tool that assumes that a developer's input is correct is going to be reasonable. We have to design debugging tools that actually don't make that assumption and start from some really clear knowledge that we're sure the developer actually is certain about. And so tools like breakpoint debuggers or even time traveling debuggers that record an execution trace and let people navigate through it, they're really only useful to the effect that a developer has a good hypothesis, right? And some of my early observations had shown that people don't really have good hypotheses. It takes them many hypotheses before they develop a good one. And so the one thing that seemed relatively reliable was that developers did know that some output was wrong. That was the one thing that most of the time they were certain about, and most of the time they were right about. So any tool that assumes that a developer knows more about a defect than just whether the output is wrong would probably be garbage in, garbage out, only amplifying some bad premise of how the program had been built. So the aha was this: what if a debugging tool could start from that unwanted output, that reliable piece of information the developer had, and then automatically identify the things that had caused that output or prevented the output that they wanted from happening, and then present that to developers to inspect and to see if they could search within that much smaller set of causes of program output to find the thing that actually caused it to go wrong. And so that idea just raised a lot of questions. How would developers identify the output? How would the system identify the causes of output? How would the system present those causes to a developer to help them carefully analyze them, right? These were all of the sort of downstream design questions that came from this empirical observation about how debugging was working. And so if you look on the right, it's basically a bunch of wild flailing sketches about all kinds of ideas about how this might work. There were random kinds of filter ideas, temporal masking of things, other overly complicated visions for how something might prevent causes of output being wrong. And so really the ideas that I settled on were things where somebody might just be able to point to the output, right? This thing on the screen is wrong. This number is wrong. This should have happened, but it didn't happen. So there was something that appealed to me, especially the HCI researcher in me that's concerned with things about the directness of the way that people interact with computers. And so the idea was point to something and then ask questions about it. Why are you here? Why didn't you appear? Why are you 5 instead of 2, right? These kinds of questions that interrogate the output, and then have that query be something that generates some computation. And then the system could tell the story with that computation. Like first this happened, and then this happened, and then that output happened. So were any of those things in that chain of causality wrong? And so you'll see in my sketches, there were just lots of ideas about showing these chains of causality and triggering those chains based on some question about some output that somebody was uncertain about. So a huge part of this was me doing that reading that I'd mentioned I'd done. And there was this one 1994 paper that I'd read called Program Slicing by Mark Weiser. And he'd made a really similar observation to me, that developers are constantly looking at pieces of some execution, whether it's a program in a static sense or a dynamic sense, and saying, where did this come from? Where did this value come from? What affects this variable? I just came to a different aha than Mark. Mark's conclusion was that the best way to support this reasoning would be to do some static analysis or dynamic analysis and try to understand all of the things that affected the program. And so a slice was this vision of, give me a variable and I'll give you the 300 statements that could possibly determine its value or did determine its value in a dynamic sense. So my aha was different. It was not give me a variable, but it was give me some output and start from there and then do a slice on that instead. And this was really critical because the slice, as Mark had envisioned it, and as hundreds of researchers had followed to build upon his work, showed that slices were just too big. They were too hard to comprehend. And so my idea was, what if this was just a bad interface for reasoning about slices? We just need a better interface for doing that. And so that's how I came up with the Y-line, and the basic design emerged. We analyze the program for all of the output statements. We create some structure that says, here's all of the output statements you might ask a question about. And then somebody could choose that in the form of a question and say, well, why didn't this output statement execute, such as this line, why didn't pack resize 0.5? And then once they've chosen that, use that query to compute a precise dynamic slice using an execution trace, and then show the slice to the developer and have them choose which part of that slice seems faulty and use that as their diagnostic process to understand causality in a more limited and scoped way. And there was lots of implementation to do, right? And so I had to replace the runtime to generate an execution trace. I had to change the IDE to expose output statements and present these answers. I had to create some visualization of the slice to convey causality. I spent a couple of months building this and showed it to my lab mates and my advisor. And most of their reactions were really positive. They said, well, why hasn't debugging always worked this way? And so the kind of face validity reaction of, does this seem useful? Does this seem reasonable? Was really positive. And so that was encouraging. I thought maybe that's enough. And it's really important to point out here that sometimes in a lot of research settings, this is where we stop, right? Something looks cool. It seems like it's useful, right? Seems like is often our strongest evidence that we'll use for some inventions. And in HCI, that's very rarely enough. Seems useful is probably the weakest evidence that we would ever consider for something. And so the next step was really thinking about whether it was, right? But while I was doing this, I hadn't thought about evaluation at all yet, right? I was very much in the inventor mindset. How might this work? How can I implement this? How do I make this scalable and performant enough? I had to step back from evaluation to really do that work, right? It was a very different mindset than the empirical work that I'd started the project off with. And so that brings us to this third chapter. How do I know if it works, right? Seems useful, isn't strong enough evidence. So what's better evidence that would be more persuasive, be more certain, and be more grounded in some of those empirical observations that I'd made before? And so this informal feedback that I'd gotten, my advisor thought it was cool. My lab mates wished they had it for other languages. The Alice team wanted to merge my branch. All good signs, but would it actually help with debugging? If I put it into somebody's actual work, would it actually facilitate their work? Those are not the same thing, right? All of these sentiments above are really not equivalent to somebody actually being able to successfully use it to diagnose some failure. So one idea I had was to just do what I'd seen happen a lot in programming languages and software engineering, and that was a benchmark study, right? I could find a bunch of defects that people had created in Alice and try to compare the amount of work entailed to do the debugging with the Y-line and without the Y-line, right? And so you'll see a lot of benchmark studies that kind of think about work in these sort of reductionist ways, right? you only have to look at 10 lines of code versus 2 lines of code, right? So there's sort of proxies for the amount of work that these studies will do. And then I could just show empirically through some analysis that the Y-line would take less work, whatever my measure of work was. And I found this personally really unsatisfying, right? And especially because of those empirical observations that I'd made earlier on in my work that showed that it was completely, the amount of work was completely dependent on all of these factors, right? How much a developer knew, the sequence of their actions, other context that was happening in the lab, whether they were noticing things. So it seemed unreasonable to make assumptions around what would constitute work and how work would be different between different developers depending on their situations. And I needed to understand those dependencies to really show that something would actually be consistently valuable in similar situations. Another study idea I had was doing something task-based. And so the idea here is select some program or set of programs that have a defect in them, run a controlled experiment where there's a set of developers that don't use the Y-line and perform that task, and a set of developers who do use it and try to solve those same bugs. And then show just through standard statistical hypothesis testing that the Y-line caused significantly faster debugging. And this is sort of a classic kind of controlled experiment that you'd find in lots of HCI papers, lots of software engineering papers, any kind of clinical trial in medicine. And this would be fine, and it's sort of a gold standard of evidence within empirical work, but it would be really highly dependent on the task that I selected, right? And prior work had shown that debugging time was highly variable between people and between tasks. There was a risk then that this variation would just mask the effects of the tool. And so I didn't go down that path because I was really worried about just understanding the range of tasks that this might be useful on, not just understanding its utility for one particular hand-selected set of tasks. And so the third idea, this is the one that I went with, was more of a specification-based evaluation. And this is the idea that I would give developers some set of requirements to meet for some program, have them go build that program, and then organically stumble upon defects that they generated and had to debug, and then just hope that they would generate defects that were similar enough to each other in terms of the structure and design of the program that I'd be able to compare them. And that of course was a risk in its own right? They could have all generated such idiosyncratic defects that I wouldn't have been able to compare anything, but at least I would have had lots of examples of people using the Y-line to debug those different defects. And so that was sort of the different risk that I took here. I was hoping that there'd be something comparable, but my default backup plan was that if there wasn't, I'd have lots of good cases to talk about. And then this had the advantage of being more ecologically valid, right? Because this was real programming work. It wasn't structured by a particular task. It had a high level goal and people could move in many different directions. It allowed me to measure task progress though, because I had a well-defined set of requirements that they had to meet. And so this is the one that I went with. And so here was the spec on the right. I had people basically making a fairly simple Pac-Man game in Alice, and most of the requirements were fairly orthogonal to each other. There were a few dependencies here and there. And then I basically counted progress based on how many of these requirements that they'd met. Now you might be looking at that bottom left paragraph here and saying 9 participants seems like a really small number. Why only 9, right? And to be honest, the reason it was only 9 was because this was 2 weeks before the Chi deadline that I was planning this study. And so this was like, can I learn something in 2 weeks and write this Chi paper before the deadline, because I really want to share this work and I'm impatient and I don't really care about getting a larger number, right? So, this is what it looks like to design studies sometimes, is you cut some corners because you're not certain how to balance and trade off those things with other priorities that you have. So I found 9. I gave 5 people the Y-line, and then I guess there were 4 with the other version of Alice. And then I gave them a 15-minute tutorial on how to program in Alice. They were all novices to the language. And then another 90 minutes to make this simple Pac-Man game. And it's important to note here that Alice is not a complicated language. It's got a very small number of constructs. It's got a syntax-directed structured editor, so you can't make syntax errors or type errors. And so there's a lot of error prevention at play. So really, it's all about the logic of the program. And so the results were really positive. I found 6 distinct defects that occurred in both of these different groups. So I found really, really different kind of task profiles and really different defect profiles, but enough commonality that I thought that they were comparable. And when I did compare them with the Y-line, people were about 8 times faster. So the range here was 10 to 40 seconds for those 6 defects compared to 49 to 330 seconds for without the Y-line. So much, much faster, an order of magnitude. And when I really looked at the video recordings of their debugging, most of this effect was due to preventing those long investigations of wrong hypotheses, right? So what I'd earlier seen in my observations, that people were spending a lot of time investigating things that were just not the problem. With the Y-line, all of those went away. The very first step that they'd done was investigating something that was the problem. And all the work that remained was to understand which part of that causal chain that had caused the problem was faulty. And since those were often short chains, they just had to go and look and see, is the 7th event in this 15 event chain wrong, and inspect each of them individually. And so participants, if you look in the caption here, they were particularly excited about this question menu at the top and its ability to instantly link questions in their head to the code that it corresponded to. And that was this really interesting phenomenon of having them ground their hypothesis in code, right? So it was no longer something where they were speculating about possible patterns of computation, but rather saying, did this line of code execute when I thought it did? Or why didn't this line of code execute when I expected it to? And so again, there were lots of caveats. If you look on the right here, it was a small sample, they were small programs, there was a really constrained, simple specification. All of them were novices to Alice, and some of them were novices to programming in general. And the language was relatively simple. Of course, within HCI, evaluations are meant to shape ideas, not to prove them useful, right? So this evidence that we had was not evidence that the tool is good and everybody should go build it now and everybody should use it, but rather that the tool has promise and that there should be more work on it, right? So we use studies in this incremental way to try to decide, should we invest more time in investigating something, or should we abandon it because it doesn't seem to have much value? So even within those limitations, that's what we learned, right? There was enough promise here that it was worth thinking about this further and thinking about it more, and that others maybe should spend some time thinking about it too. But the study also revealed why it worked, right? Linking questions in a developer's mind to code and execution history in a way that narrowed the prospect of what they had to consider and grounded in data that they were certain about, which was their program's output's faultiness. That was a really powerful way of searching for defects much more rapidly. That's how and why it worked. And so stepping back from that evaluation phase, right, note that the goal of the study wasn't to prove that the Y-line was better, but whether it was and why, right? It was really formative evidence, not summative evidence. And so step 4 here, this is an interesting one, and it really starts off with feedback that I'd received from presenting at CHI. It led to a lot of questions. There were fans of the work who learned about it through the press and wondered about other programming languages. For example, this person, I forgot to blur out their name, was in the Allegheny County jail and was doing a lot of programming as part of a work study program. He was asking about how I might use the tool for all of these other languages that he had. Software engineering researchers wondered about scale and complexity. Programming languages researchers wondered about the risk of helping too much and weakening developers' debugging muscles. Lots of companies had asked about the implications for their own language stacks. And so my first reaction to this was not to jump in and start working on that problem. And the context was important here, right? This was my first year of grad school. This was the second paper that I'd published. I wasn't ready to commit to the Y-line to being the entirety of my dissertation, and I certainly wasn't ready to graduate, even though everybody was really excited about the work. And so I decided to play for a few years and go learn other things and do other stuff and gain more expertise. I studied API learning. I studied people using IDEs and how they affected productivity. I designed and built a programming language. I studied interruptions with collaborators. I built code editors. I did a Y-line for user interfaces, not for programming. And then I interned at Microsoft Research and spent a summer trying to understand how developers work on teams to exchange information too. And so that pause for 3 years on the Y-line work just taught me a ton of things that made me more capable of doing better work later. I learned more about the architecture of programming language stacks. I learned about the architecture of IDEs. I learned a whole bunch of qualitative methods. I learned how professional software developers do their work. And there's an important point here, which is that I went straight from undergrad to grad school. I hadn't even worked as a software developer before. I'd programmed plenty myself and with other people, but never been in a company. So that was really essential. And I also learned how to publish in software engineering venues too, right? Which is a very different thing than publishing in HCI. So all of these really shaped my understanding of what a Y-line for a general purpose programming language would need to be, helping me gain research method skills and identify requirements and better understand software engineering. So when I came back from that Microsoft research internship, I felt really sure about what I needed to do. So I prototyped a bunch. You can see screenshots of those on the right showing different ways that this might work for a general purpose programming language. And I chose Java in particular. This was the most prominent language at the time, especially in software engineering. And so my thesis proposal talked about that. It talked about everything I'd learned. It had pseudocode for the algorithms I proposed to investigate, a study design plan for precisely evaluating the effects of the tool, an 18-month timeline, a bunch of engineering plans. It really was a specification for my dissertation work, as fully as it could be possibly fleshed out. So in a way, I felt like my plan 3 years later was much better than the plan I would have come up with right after that first step. And so the next phase was really 9 months of engineering and design. I rebuilt a JVM to do a bunch of precise bytecode instrumentation. I built an execution history format that would support real-time compression and organized it for incremental loading and random access. I built some incremental static and dynamic analysis engines for doing all of the analysis work. I built an output history viewer that would take the subset of history that was concerned with pixels on the screen and use it to create a video of everything that was happening during program output. I built a repository and history viewer to support questions and answers and browsing and searching. And then, interestingly, for the study, I built a breakpoint debugger within my infrastructure so that everything would be identical to the Y-line interface except for the interface for investigating the trace. And then really key, because I was an HCI researcher, I was doing usability evaluation constantly. So every week I would take what I built so far and put it in front of somebody and see what they were stumbling on and fix all of the usability problems that they were bumping into that would have gotten in the way of them getting value from the tool. I also, in contrast, did weekly usefulness testing on a growing corpus of defective open source Java projects. So I would go through and run through a corpus of about 15 different defects and see, can I use this tool yet to find the defect easily? And then within the context of all of this, I think it's just important to point out life too, right? I was getting divorced at the time. Programming was a good escape, but not a very healthy one. And so I was really trading off a lot of my mental health for focusing on this engineering work. And if I had to do it over again, I probably would have just taken another pause and spent another 9 months giving myself the time for my life to stabilize a little bit before jumping into all of this work. But I didn't do that. It worked out fine anyway. And then by the end, I had a release candidate. After 9 months, I had this prototype that was stable and fast and usable and appeared to be useful. Again, I didn't have evidence of that on a corpus of defects. And there were a couple of things that I was really certain of by the end. It was novel, it was a huge amount of engineering work, and I was really proud of it. But there was one thing that I still remained highly uncertain of. Would it actually be useful to Java developers trying to debug some defect? Note here that the evaluation of usability and usefulness was really iterative, right? It was embedded in this design process. It was not an afterthought. It was something that I did while I was designing and building the tool, not something that I fixed afterwards. So that brings us to the last phase. Does this really work? So the critique of that first evaluation that I'd done is really basic, right? Small samples, small programs, novice programmers, simple language, All of these things dissatisfied the software engineering community. They were not at all considered acceptable by the evidence standards in that community. And so I needed to really rethink, if I was going to publish this to software engineering, what might this look like instead that would work at scale? But not only scale, but complexity. So I wanted to do something more naturalistic, as with the Alice study, but I wanted to think about how to do this in a way that was reflective of something that was real. So I decided to go with a controlled experiment to appease reviewers and not risk my upcoming academic job search. And the basic idea here was that in software engineering at the time, virtually nothing other than a controlled experiment would have been acceptable. And so I had to really trade off that ecological validity for something that would be accepted by the community. And I didn't want to sort of fight that battle and try to make sure that there was a broader kind of evidence accepted. And that's changed, of course, since, but at the time, it really was the only acceptable form of evidence. So the study design was a classic controlled experiment. It was between subjects. There was a group that got the Y line and a group that didn't. There was training to introduce all of the participants to features of the tool. I recruited 20 participants and split them evenly. They were all recruited from the Carnegie Mellon Masters in Software Engineering, and all of those students had, by requirement for admissions to the program, at least 3 years as a software engineer in industry. And then I chose a couple of tasks from an open source project called Argo UML, which is about 150K lines of code, and 2 real defects that were reported in its bug repository. One was removing a deprecated checkbox and all of its associated functionality. And another was fixing a drop-down menu that was missing an item. And these were chosen intentionally because of their complexity, the amount of cross-cutting concerns that they touched on in those 150,000 lines of code. And also, especially the second one, debugging something that was missing rather than something that was present. And that's always known to be a harder task, and the Y-line was trying to help with that as well. And so I told participants that they were new hires and that they were just assigned these bugs as warm-up tasks, and they had to write a change recommendation for a patch and to prioritize correctness over speed. And it was useful. They were a lot faster in the first task, about the same in the second task, but largely more successful on both tasks. Nobody succeeded for task 2 without the Y-line, and about half of them did with the Y-line. And then lots of basic qualitative feedback, like they love it, they thought it was great, they thought it would really help, when can I get this for C, and so on. And so lots of really good praise for that work. So this was really, in some sense, a replication of that first study, right? Slightly different methods, slightly different people, different implementation, but really it showed the same kind of results. Well, why was it useful? His study revealed a couple of things. One is they spent more time inspecting more relevant files and functions. They avoided unproductive guesswork, just like in that first study. They spent more time carefully reading the semantics of relevant code rather than doing kind of random searching. And so it led to this theory, really, which was that strategies shape whether a developer debugs productively, so how they go about doing it. But tools shape the strategies that are possible, right? The strategies that are possible with breakpoints are really different than the strategies that are possible with something like the Y-line. And I found that breakpoint debuggers really promote this unproductive kind of risky guess-making. I think it's this, I'll just set some breakpoints, and it just leads to this mess of investigation. And the Y-line promoted this really productive, focused, and empirically grounded strategy of, I know this is wrong, let me systematically go through and see which part of it contributed to it. Lots of good things happened afterwards. I presented the work and won a distinguished paper award for it. It led to lots of consulting gigs with language maintainers, Microsoft, Mozilla, Adobe, and Apple. So I spent a lot of time with those companies trying to understand how this would play out in their language stacks, and learned a lot more that I never published about the challenges of implementing it, the difficulties of making it work at scale. That sharpened a lot of my knowledge. And then 10 years later, I won a most influential paper award for a lot of this and got to reflect on what I learned. So let's reflect now on what we've learned from this story and just wrap up this talk. One point I made here is that we often use the phrase user study, especially in programming languages, as if it's merely just a subtask of publishing. This dissertation story should show you that user studies are about a lot more than that. It's about discovering opportunities for invention, requirements and constraints for what you invent, but it's also about discovering explanations of the value of what you've made. Why does it work, right? In addition to getting evidence of its limitations. And so I would put this pretty strongly. I'd say if you don't observe people using what you've made, you really don't know what it is or why it's significant. You've just made something. It doesn't really tell you anything more than that. The second point here is that one study is not enough. My dissertation story showed that when you do 2 studies, it's not even enough, right? Even with that highly controlled experiment that wrapped up my work, it was 1 code base, 20 developers, only Java. I honestly just still don't know, even after all of that consulting, whether the Y line is useful in practice 12 years later. A lot of companies built out a lot of their stacks. They never quite got to the point of building debugging tools on top of those stacks. That doesn't mean that the evaluations are worthless or that consulting was worthless. It just means that our knowledge is incremental, right? We get an accumulation of evidence over time that something's valuable. And so there's no better time to start accumulating that evidence than now. It should also be clear from this story that study design is really situated. I did this study that made sense for the tools that I created at the time, for the resources that I had, for the people that I had access to help me, for the skills that I had, for the audiences that I was speaking to. There's no best study design in any of these cases. There's just the study design that you're most capable of doing and that answers your question and that serves your other goals. And this is really important because searching for the perfect study design isn't really going to be fruitful anyway. You need to have many studies of these things to really understand them. And then of course, study design is complex, right? I had to account for hundreds of factors, and this necessarily requires careful, slow, thoughtful iteration and test runs and piloting and lots of time to make sure that you really understand what's happening. So do study design slowly, do it deliberately, do it with the help of an expert. It's always going to turn out to be more complicated than you think. And then finally, HCI really is about more than just evaluation. Many people in programming languages appear to view HCI more narrowly than that. But it's important to recognize that HCI methods are integral at every step, but the broader discipline is a much larger thing. And what that means is don't go to an HCI researcher, as people often do to me, and say, please design my evaluation for this thing that I've made, right? That's too late, first of all. Right? Because by the time you've done that, you've already prevented the possibility of any of the knowledge from HCI shaping what you made in the first place. And second, it disregards HCI researchers' expertise, right? Which is about much more than just the invention, just the evaluation. It's about the invention of novel forms of interactive computing and evaluating them and understanding their impact on the world, right? So thinking about it narrowly like that doesn't really help anybody. Now, if study design is hard, how do you learn how to do it? Well, you start really by reading, right? This talk, if this is the first time you've thought about this, this is just a pointer into lots of other places to learn. And there's a few resources I can point you to help you learn how to make good study design decisions, to think about caveats and confounds and challenges, factors to plan around, and how to iterate on your design. Let's start with this one. This is one of my favorites from about 12 years ago. This was published at CHI. It was called Usability Evaluation Considered Harmful Some of the Time by Saul Greenberg and Bill Buxton. And they talk about how the choice of evaluation methodology really should arise from the actual problem or research question under consideration. Looks like there's an incomplete sentence there. Not some sort of desire to check a box for publication. Right? If you do it that way, you're really only going to end up with a bunch of useless knowledge that doesn't really advance our understanding. This is a book chapter that I wrote last year with Sally Fincher at Kent in the UK. What we tried to do here was talk about how do you go about designing studies? What is the process that you follow for that? So we identified lots of strategies for doing that, really critical questions to ask to shape your understanding of what is the question you're asking and why is that question meaningful? And is it interesting, sound, and important and novel and so on? And so a lot of people have used this over the past couple of years to really structure and shape their understanding of whether their question is good. My student and I, a couple of years ago, Greg Nelson, published a paper on the use of theory here. And so theory in a social science sense, not theory in a computer science sense. And this paper talks about the importance of using theory to inform your design and your evaluation, but also the perils of relying on it too much, in that it can sometimes prevent you from being creative. And so I hinted at this earlier in the talk, where I talked about needing to think as an inventor sometimes and as a scientist and other times. This paper is really talking about that in relation to theory. There's a paper that I wrote with collaborators Thomas Latoza and Margaret Burnett, who I'll note was my undergraduate research advisor from quite some time ago too, so I still collaborate with her. This paper describes lots of the things you need to know to design a good experiment, to study a developer tool. It also kind of passively argues that you probably shouldn't run a controlled experiment, and talks about why, but it should become self-evident from all the complexity of doing it and the limited knowledge you can gain from it. But if you do decide that you need to do it, this is a good guide for doing it. And then I'll go all the way back to a paper that I wrote. This is the first paper that I wrote as an undergraduate, on how to make sure that your experiment isn't confounded by usability problems. And so this was an idea of using an older HCI method called cognitive walkthroughs to identify problems in your tools and in your tutorials, to make sure that those problems don't get in the way of somebody actually getting value from your tool. And so this was really kind of a nerdy research methods paper that talked about a way of making your research methods work out better for you. Just an interesting contribution. And then lastly, I'll point to another UW student's work, which was looking at participant response bias. And I think this paper is really important because it talks about the risks of evaluating your own tools. It turns out that almost consistently, always, when you go to somebody and say, here is a thing I made, it doesn't matter what you have them do or how close you observe it, they will be more likely to give you positive feedback about that thing that you made, because they don't want to tell you something negative. And this happens even more systematically the less technical expertise somebody has. And so we have to think really carefully about who is actually doing the evaluations that we do. Can it be the inventor, or does it need to be somebody who's more impartial? So consider all of these things the beginning of your learning. Knowing anything about programming is really hard. Just keep reading, keep practicing, keep reflecting on what you're doing, and this community will be here to help. Thanks for your time.
Thank you.
I love the muted Zoom applause.
Thank you so
Little
much,
sound.
Amy.
Thank you, Amy. That was awesome.
Man, I was taking furious notes. So, all right, everyone, it's time for breakouts. I am going to randomly, oops, let's see, hold on. Sorry, I should have practiced the making of breakouts.
I've got it here. Do you want me to do it, or?
Yeah, looks like I don't have.
Okay, let me take care of it. So let me put people into, okay, so there's going to be 13 rooms of about 8 people each. We're going to give you about 10 minutes. Partly we will circle around the rooms and come and see how the conversations are going. But we're not going to go over 10 minutes, but if we're starting to see things tamping down a little bit, we'll bring you back. Because we also want you to have plenty of time to ask Amy questions and hear Amy's answers. But remember, the goal is to try to consolidate your questions, okay?
All right. I believe we have almost everyone back. We're back up to 100 participants. So I'd like to open the floor to questions that are inspired by your discussions in small groups about, what you found surprising, what you're not sure to do next, given Amy's calls to action and wise words of advice, and anything else that has that was unclear. So please raise your hand, and I will attempt to call on you, and you can unmute yourself and ask the question directly to Amy. Okay, Will, go ahead.
Great. So, hi, Amy. Thanks for the awesome talk. Our question was about adoption and getting your tool out into use. And you mentioned that you had worked and consulted with several places and trying to get the relevant, the relevant runtimes instrumented, and that along the way, there were some struggles in getting this tool, which, you know, to many of us seems like you an obviously good idea. But we're curious if you could just talk more about what were the challenges in getting it adopted. You know, was it, you know, the application domain? Did it end up being there was too much reliance on it being a graphical application and it was hard to generalize to other contexts? Or, you know, what other kinds of factors might have been at play in getting this into the real world?
Yeah, sure. I guess I'd summarize that and say that because organizations, so organizations have all of these other challenges and constraints, right? They have business priorities, they have money they need to spend, they have engineers that have certain capabilities, they have roadmaps and priorities and all of these other things that exist in software companies, right? So each one of those different companies that I worked with had different organizational constraints that made that more or less easy for them to make progress. So an example was Microsoft at the time, in 2009, when I started consulting with them, they had already started building internally something called IntelliTrace, which was just an execution tracing engine for all of their .NET platforms, right? And so when they saw my work, they said, that's why we're building this. It gave them fuel internally to say, here's the kind of thing we want to be able to make with IntelliTrace. And so it meant more resources for IntelliTrace, a larger team, faster progress on building out that infrastructure, a lot more excitement to do that work. And then I think 3 years later, 3 or 4 years later, they dropped .NET, right? They said, this is not a priority for us anymore. And so because of that market consideration and because of that internal decision, IntelliTrace was no longer this thing they wanted to invest in anymore. They were like, it's fine where it is. We're not going to build anything higher on that stack. We're still excited about this vision, and maybe we'll get to it some other day with this other stack, but this stack is now a low priority. In contrast, when I was talking to Adobe at the time, Flash was still really big and really ubiquitous on the internet. And they were talking about building this on top of the Flash stack. And that had other challenges because of its architecture, right? A very legacy kind of non-standard PL architecture, all kinds of strange things about the runtime. So they perceived a lot of difficulty doing that in the context of that particular architecture. And then, of course, they abandoned Flash, too. So all of the work that they'd done to think about what that would look like just disappeared as soon as Flash was gone. So none of it was really about thinking the idea was intractable or not generalizable. Most of it was just about those market considerations and about business priorities. And that's a different set of challenges. It's really something that we can inform for industry, but we can't really change those circumstances.
Great, thank you.
Wonderful. So next up is Josh Filstrup. Go ahead, Josh.
Hi, thank you so much for the wonderful talk. As someone else on the West Coast, I really appreciate you giving a talk this early. One question I had that we discussed in the group is also about translation into industry. And as you try to translate this into a real tool, say VS Code or any kind of popular editor, what are ways you think we can go about kind of gaining metrics and understanding about the usage as it translates to a much broader audience? And how can we kind of glean information from that?
I think I'll answer this using some business terminology too, and say that in industry, the standard way that you gain insight into how people are using your products are a bunch of different disciplines. One of them is marketing, one of them is user experience design, some of them are customer experience and customer support, and all three of those different channels have different methods for learning what people are doing with a product and what's working about it and what's not. Marketers will use things like focus groups and gather large scale data. UX designers and researchers will do a lot of qualitative methods and really observe people using products, kind of like I talked about. And then people that are doing customer experience and doing data science on that data, they'll be looking at things like discussion forums and issues that are escalated to bug reporting systems, other kinds of log data analysis. So there's just many, many ways of knowing. And all of those in some ways mirror the ways of knowing that we have in academia. They're just put into practice to making sense of products, right? That all assumes, of course, that you actually have a product and that it's being used. And so I think there's a challenge there, especially with programming languages, about getting adoption to happen in the first place and then having some data to observe. I think Google's a really interesting example of this right now with a lot of internal languages. and ones that are public but mostly used internally, like Go, right? They have amazing log data about how their language is being used and all kinds of other mining that they're doing on it. But they had to really get adoption to happen first before they could do any of those things.
Great, thank you.
Wonderful. Next up, Slim, one of our social organizers, is in line to ask a question. Go ahead.
Yeah, so we had a question that was from our kind of focus group in general. Rashab asked, basically, in a situation where you have two similar languages, I think the example in this case was CUDA, for one of them, where one of them is like longer lived, has a larger ecosystem, and just generally more ties to applications and industry that are, just very deeply rooted. And then you have another language with that does a very similar thing, is maybe newer, has a better developer experience, things like that. What is the research show on like how we might get people to like shift to or adopt a new language, whether that adoption or shift is even likely to begin with, and like what are factors that people use to decide where the center of gravity in an industry should like shift?
Oh, that's such an interesting question. Let's talk about adoption more deeply. Adoption is not about persuasion so much, right? I mean, you can come up with good evidence and you can come up with good arguments for why somebody should use one thing over another. It's really about behavior change, right? If you worked as a developer for 20 years on a particular stack with particular technologies, think about the immensity of learning that has to happen to shift away from that. The value of some new thing has to be so greatly higher than the amount of effort involved in that learning that's required. Sometimes to make big leaps happen and make big changes happen, you either have to capture the attention of people who are just at the beginning of their learning, such as students or other people who are learning to program for the first time, because then the cost is nothing, right? It's perfectly comparable between one or the other. It's really just about evaluating communities and other things. But if you're talking about taking somebody that already has practices and already has knowledge and already has all of these skills for one platform, and making them change it, it's going to have to be very valuable. The only exception to that is when somebody can unilaterally just cause a change, right? When an organization says we're going to use this instead of that, and then all of their engineers have changed, that can be something that moves people really quickly. And you've seen this happen at places like Apple. You've seen it happen at Microsoft in some ways, where large software companies say, this is the new thing. Get to learning and get going, and that's the new platform, move on. So I think there's a lot of factors there that are really about what are the things that actually cause people to reconsider their skills and abandon knowledge and move on to new knowledge. And a lot of those things really are not about great programming language design. That's a necessary but insufficient thing to get somebody to change their behavior.
Wonderful. And a great example of what we are hoping to come out of these discussions is that you were able to ask a question based on the entire table's discussion. All right, Daniel Wang.
Hi, thank you for such an energetic and inspiring 8 a.m. talk. Doesn't sound easy. So our breakout room had a question about user testing. So sometimes user testing requires approval from an internal review board, IRB. And that tends to be a really lengthy waiting process, like for them to get back. And since user testing is iterative, how do you iterate quickly when IRB approval can be a bottleneck sometimes?
Oh, that's a really interesting question. Thanks for raising that. So for those who don't know, in the United States, there's something called institutional review boards that are mandated by federal policy about ethics guidelines for human subjects research. And so there's a certain set of definitions of which kinds of studies have to be reviewed by these panels to verify that they are ethical and that the cost benefits of them are worthwhile. And so that takes some time to analyze. And sometimes that means writing an elaborate description of your research design and your plans so that somebody independent from you can evaluate its ethics and make sure that there are changes that might need to be made to preserve anonymity, for example. So within that whole process, right, what I find is that when I ask students to go write down their plan for an IRB approval, that's part of the iteration. the first time they write it down, they realize they don't really know what their plan is. They don't really know what they're going to do. And they learn through the process of just trying to articulate it that some of their details are really not figured out yet. And so that leads to iteration and leads to a better design, right? And then by the time that we have a specification that we're ready to submit to an IRB, there's a decision there about whether or not to evaluate before or after approval. Sometimes I'll have students say, okay, take the plan in your IRB and let's go pilot it. Let's go find out if that's good. This is what people will do in other disciplines, right? Take the time to make sure and verify that the plan is good. And then once you're certain that it is and you've iterated enough, then you go off to the IRB. And the key part of that is that, are you doing human subjects research when you're doing that piloting? Right? If so, doesn't that need to be approved? And the challenge there is, well, can you find groups of people in your lab, for example, where there aren't anonymity concerns and where there aren't data privacy concerns, and you're not going to use any of this for publishing, where there's maybe even a research team member that's going to play the role of a participant and then step through it that way. And then, of course, IRBs vary in their timelines. I think ours have gotten to the point where we get usually 3 or 4 days turnaround, and because they're really oriented towards supporting iteration. Others can be longer depending on the risks. And so you'll really just have to strategize around the risks you're willing to take on in planning that and having the uncertainty of an IRB's evaluation timeline.
Wonderful. Next up is Chris Martins.
Hey, fantastic talk. Thank you. So our table or breakout group was kind of started by discussing this point that you made in your talk about, if you start out by saying, okay, I've built something, hey, HCI person, can you evaluate this for me or help me come up with my evaluation? Like, that's too late, right? And so we were all chatting about just kind of, okay, well, what is the right way to approach either, collaborating with HCI folks if you're coming from a place where you're not well suited to perform those activities yourself, or perhaps, in which situations does it make sense to actually become the HCI researcher you want, right? And learn the skills and incorporate them into your tool set.
Yeah, that's such a great question. Thanks, Chris. Both are viable paths. And sometimes, in a way, if you think about collaboration, interdisciplinary collaboration, the latter path is a necessary one, because to even be able to collaborate with an HCI researcher, you have to understand what makes HCI research. Otherwise, you won't really know what's going to be valuable to them when you're doing that work. So you have to have some knowledge of other research areas to even be able to start that conversation. I remember an example where I was seeking a social psychology collaborator, and I had to do a bunch of homework on what makes social psychology research novel. And I just stumbled upon this idea of, like, they only really care about novel hypotheses. That's the thing that drives their field. If you can think of some interesting possible explanation of some phenomena, then they'll write a grant proposal about that. So I had to come up with a novel hypothesis before I could even reach out and say, hey, I had this idea for this novel hypothesis. Do you want to investigate it with me? So the same thing for HCI would be coming to an HCI researcher and saying, I have this interesting kind of new interactive computing that I'd like to investigate with you. I think that there'd be this really promising thing for us to look at together, right? Or I'm really curious about the impacts of this technology, but I want to design it from the outset with those in mind, right? Depending on the kind of HCI researcher you're talking to. So interdisciplinary work like that does require kind of mutual learning and some mutual understanding of each other's fields and finding shared goals that will help each person. HCI is easier than other disciplines because HCI knows what computer science is, right? It overlaps greatly with it. So there's not as much work to do there as if you're going and talking to somebody in some entirely different discipline.
Thanks.
Absolutely. Next up, JD.
Hi, thanks for your wonderful talk. I really enjoyed it. This is a bit of a softball question, so my apologies, but we were curious, you mentioned early in your talk about how you came about starting to investigate debugging, and I'm wondering, are there other things that you sort of also noticed around the same time that you either dropped because you ended up focusing on debugging as sort of this critical piece of the programming enterprise? I wonder if you could talk a bit more about, like, in the scope of things that you could have worked on at that time, how you selected that one?
Yeah, sure. I'll tell a fun story about statistics. So my undergraduate thesis, the year before I started grad school, was studying, really studying debugging in the context of different statistics programming environments. And so at the time, it was things like SPSS and Stata and a couple of other things. And I ran this big experiment where there were different platforms that people were programming on and doing the same kind of hypothesis testing. And so I was really excited at the time about, like, what would it look like to create some statistics programming environments that would better facilitate domain knowledge about statistics, but also facilitate experiment design and really careful reasoning about data and other things. So I went to my advisor and I was like, what if we built platforms in which people could write programs that process data and reason about data more in more principled ways? We could call it, like, I don't know, data methods programming or something like that. And he was like, that sounds like a terrible idea. Why would anybody ever want to do that? And then, of course, like 5 or 6 years later, people are like, data science, yay. This is an example of, you know, your advisor doesn't always know the future. You don't always know the future. You can't really know whether your ideas are good at the outset. Like, my advisor raised real good limitations of why doing statistics programming would be this really uninteresting thing at the time. And he was probably right? I was probably just a few years too early to really push on some of those things. And so there are always going to be threads like that where you don't pursue something and you see something pop up later, and you should just be excited that your community is noticing the value of some of those important questions and not really disappointed that it wasn't you. Because it's really not about us as individuals at some point anyway. It's really just about us as a community and what we're discovering together.
Next up, Tyler Holloway. Please go ahead.
Hello. You touched on this a bit with Chris's question, but one thing our group talked about was when you're doing such interdisciplinary work, how do you personally split your time between studying and testing the educational pieces, for example, and then also the more technical pieces?
Oh, that's a good question. Thanks so much for asking. I find that that's a very personal kind of process. So I will, do a bunch of studies and really understand something cognitively or socially for a while. And then just one summer, I'll just get this itch and just feel like I need to make something. I've learned too much and I have this knowledge that has to burst out in the form of some artifact, right? And then I'll spend a summer building something or recruiting a PhD student that we can build together on some vision for several years. And at some point I get tired of the making because I realize there's so many limitations in our visions of what we're making. And I just need to go understand more too. So in a way, it's really just the duality of that in my mind. And some of that's reflected in my undergraduate degrees of computer science and psychology. I just like both of those ways of thinking and I get bored with one or the other. The most exciting thing to me about becoming a professor was the idea that I could do both at the same time, right? So I would just never be bored. I would always be making something and I would always be investigating something, and I would just parallelize all of them. And if I was ever bored, it just meant that I was more excited about talking to one student on one day than another, as opposed to waiting 2 years to do some new thing.
We've got 2 questions left. David, take it away.
Hey, so when we were talking in our breakout group, we were wondering, and when we are creating our ideas and shaping our ideas, we were wondering, like, there are so many user studies, and we were thinking on, okay, there is an explanation here on how we change from task-based user studies to specification based, and we wanted to have more details on how do we determine that our ideas are mature enough to, depending on the study. That was more like the question that we have.
I wish I could give you an algorithm. I really wish there was a procedure for these things, right? What I find tends to happen if I think about my experience is that as you develop ideas for studies you might do and for investigations you might perform, you get an instinct for what prospects for discovery they have, right? And you can kind of evaluate them against some of those things. And that requires understanding what work has been done in the past, understanding what risks there are in the study you might do, understanding the discourse that's happening in your research community and what things people are interested in, right? And so that particular book chapter that I mentioned, the study design process, that's really just a reflection of the strategies that we've used in our community to think about how do we evaluate whether or not something's worth the time to do. Ultimately, all of these are predictions, right? You can't really know whether or not your study is going to work out. If you did, then it wouldn't be worth doing. That's why we do it, right? One thing that I like to think about as a strategy in deciding that is, what are all of the things that might happen, right? If I enumerate the 15 possible outcomes of doing some study, are all 15 of them interesting, right? This is sort of a risk aversion kind of metric. If 14 of them are interesting, am I willing to take the risk that the 15th happens and then I don't really have anything to share that's interesting to people? If there's only 2 possible outcomes and one of them is super exciting and the other one is really, really boring, right? Do I take the risk on that one? So I always try to think through and reason about, like, what are the possible futures of some investigation and which ones are worth the time to take the risk on? I think that's a very general kind of way that a lot of people in any kind of scholarly discipline are going to think about how to navigate the opportunities that they have in front of them.
Thank you.
That's a great place to end. Amy, we are so grateful for your talk, all the knowledge you've shared today, the blow by blow of a very influential thesis, and for answering all these follow-ups. So I know there's many more questions that we weren't able to get to, but there will be, scroll them away. Remember, you can even rephrase them and submit them on Thursday so that we can talk about them with all the organizers on Friday's panel.
Sure.
All right.